Hey everyone, and welcome to this explainer. Today, we're taking a foundational chemistry concept and turning it into, well, a bit of a visual detective story. We aren't just going to sit here and talk about abstract scientific laws. We're going to look at the hard evidence together. We are tackling one of the most fundamental mysteries of the physical world, the mystery of the missing mass. Have you ever wondered what actually happens to the weight of an object when it seemingly disappears into thin air? Well, we're going to find out. So let's just dive right in. Think about what actually happens to the physical stuff when we dissolve salt in water or mix a bunch of chemicals together. If you take two things, weigh them, and then combine them, should they always weigh the exact same amount as their individual parts? I mean, it sounds like simple math, right? 1 plus 1 equals 2. But as we're about to see, nature kind of likes to play tricks on our digital scales. To really get this, we've got to set the stage. We're going to contrast two totally distinct types of transformations today. First, a simple physical change, where materials just mix together but fundamentally remain the exact same substance. Think of dissolving salts in a glass of water. Second, we're going to look at a chemical change, where entirely new substances are formed, like when you mix baking soda and vinegar and get that famous bubbling, fizzing reaction. Does the mass behave identically in both of these scenarios? Let's look at the data. All right, Section 1, Investigating a Physical Change. Okay, so here's exactly how we set up our baseline experiment. We take a nice clean beaker, pour in about 50 milliliters of water, and place it right on a highly sensitive digital weighing scale. Then, we add a spatula full of common table salt. We carefully record the mass of the water and the undissolved salt together. Finally, we swirl that beaker around until every single grain of salt is completely dissolved into the water. Poof! It vanishes from sight. Now, take a look at this side by side. On the left, right before dissolving, our scale reads 55.010 grams. On the right, after the salt is completely dissolved and essentially invisible, the scale reads 55.011 grams. Now, that tiny 0.001 gram difference, that falls well within standard experimental error for these kinds of digital scales. So what this visual proves is that the mass stays practically identical. The salt might have vanished from our vision, but the physical stuff is literally still right there in the beaker. Mass absolutely does not change during a physical solution. Moving right along to Section 2, a chemical change mystery. For this next setup, we're throwing it back to a classic combination you probably remember from middle school science fairs, mixing vinegar with baking soda. Now, we know this creates a brisk effervescence, a whole lot of bubbling and fizzing, which is actually the active formation of carbon dioxide gas. We place a flask of vinegar and a little balloon containing our baking soda side by side on the scale to get our absolute starting weight. Then, we pour the baking soda into the flask, let the reaction happen right out in the open air, and then we weigh the remaining liquid. And wow, this perfectly illustrates our plot twist. Look at the numbers on these scales. Before the reaction, our total mass is a solid 22.140 grams. But after the baking soda is poured into the open flask and all that bubbling finally stops, the digital scale drops significantly, down to 21.238 grams. The numbers just flat out do not match. So we really have to ask ourselves here, did almost a whole gram of matter just magically disappear from existence? Did the universe literally just delete part of our baking soda? Come on, in science, matter doesn't just vanish. There has to be a perfectly logical explanation for why this scale is reading almost a gram later. Let's figure this out in Section 3, Solving the Missing Mass. Okay, so we're going to repeat the exact same chemical reaction, but this time we're getting a little smarter about it. We put the vinegar in the flask and the baking soda in the balloon, just exactly like before. But instead of pouring it in directly and leaving it open, we fix the balloon tightly over the mouth of the conical flask using a thread. We are sealing it completely before we mix them. By doing this, we create what's called a closed system. Nothing gets in, and more importantly, nothing gets out. Then we lift the balloon, let the baking soda fall in, and watch the magic happen. And bam, the crucial point is revealed right here. When we actually trap that escaping carbon dioxide gas inside the balloon, causing it to inflate right there on the scale, the initial and final mass readings match perfectly. We are looking at 22.512 grams on both sides. By sealing the flask, we captured the invisible gas that just floated away in our previous attempt. It turns out, gas has mass. The missing matter didn't disappear at all. It just changed into a state we couldn't easily see, proving the mass was literally there all along. Which brings us perfectly to Section 4, Law of Conservation of Mass.
Now, this exact realization, we didn't just stumble upon it today. It was actually proposed way back in 1789 by Antoine Lavoisier, this brilliant scientist widely known as the father of modern chemistry. Lavoisier was incredibly meticulous. He insisted on using highly accurate balances, very much like our digital scales today, to measure absolutely everything before and after his chemical reactions. Through those super rigorous experiments, he formulated the law of conservation of mass. And guys, this is a big one. It states definitively that in any chemical reaction, matter can neither be created nor destroyed. The total mass of the reactants, so the stuff you start with, will always equal the total mass of the products, the stuff you end up with. Even if it turns into invisible gas or ash or smoke, the total weight of all those atoms remains absolutely constant.
Lavoisier literally summarized our balloon experiment centuries before we even did it. He wrote that, quote, "In every operation, an equal quantity of matter exists both before and after the operation," end quote. It's just this beautiful, balanced equation of reality. The atoms simply rearrange themselves into new structures, new gases, new liquids, but the ledger of mass is always perfectly balanced. So as we wrap up this explainer, I want to leave you with a thought to chew on. If every single atom is perfectly conserved and matter can never actually be destroyed, but merely transformed into invisible gases or different compounds, what unseen chemical transformations are silently shifting the weight of the world around you right this very second? From the rusting of a bicycle outside to the very breath leaving your lungs, the mass is always there, constantly dancing, perfectly balanced. Keep observing, keep questioning, and I'll catch you in the next explainer.